Chemical Kinetics, Part 11, Half-Life for a First-Order Reaction. Here's a sheet with all of the important equations for chemical kinetics. These are the equations that you need to do any calculations. And what we're going to do in this video is take a look at how we can take the integrated rate law for a first-order reaction and turn it into the half-life for a first-order reaction. So the half-life for a first-order reaction, where we have a single reactant A forming products, starts with the integrated rate law for a first-order reaction. Let's just rearrange this by subtracting the natural log of concentration of A at time 0 from both sides, so it moves over to the left. And then let's change this expression so it looks like this. Now, before we go any further, let's just go through why you can do that. Just a quick math review here. We know that the natural log of e to the x is equal to x. And I like to use log base 10 a little bit more because it's a little bit easier to wrap your mind around. So let's do log base 10 to the x is equal to x. So the log of 10 to the third is equal to 3, and the log of 10 to the second is equal to 2. So we could say log of 10 to the third minus log of 10 to the second would be the same as 3 minus 2. Now we could rearrange this on the right-hand side and say log of 10 to the third divided by 10 to the second. Now 10 to the third divided by 10 to the second, well, that would be log of 10 to the first. Remember that when you have 10 to the third power divided by 10 to the second power, that's the same as 10 to the 3 minus 2 power, or 10 to the first. Well, log of 10 to the first is 1. So we can say that this side of the equality solves out to be that. And that's equal to negative kT on the right. Now let's substitute in the half-life criteria, that time is equal to half-life time when the concentration at time t is equal to half of the initial concentration. So we're going to substitute half of the initial concentration in here for concentration of A at time t. Now notice when we do that, the initial concentration, or the concentration at time 0, cancels out. And the left-hand side of the equation becomes the natural log of 1/2. And now we're going to plug in, instead of t, we're going to call that t 1/2, because now we're talking about half-life time when that's true. We can punch this in the calculator. The natural log of 1/2 is negative 0.693, and say that's equal to negative kT 1/2. Rearrange it, and we get that t 1/2 is equal to 0.693 over k. That's always the half-life of a first-order reaction, and notice it's constant because k, the rate constant, is constant. So when you take a number divided by a constant, you still have a constant. Now it's important that all radioactive decay is a first order process. So when we have radioactive decay of elements, they're first order decay processes. So we have a constant half-life for those. Let's just take a second look at half-life here. Again, we have a single reactant A forming products. Here's our integrated rate law. Rearrange it to get this. Express the left-hand side this way. But now, let's do an inverse natural log of both sides of the equation. Now, if we know that a natural log of e to the x is x, we could say an inverse natural log of x would be e to the x. Okay, so we take an e to this power and an e to that power. That's an inverse natural log of both sides. This side simplifies down to be concentration of A at time t divided by the initial concentration, or concentration of A at time t divided by concentration of A at time 0. And this side is equal to e to the negative kT power. Let's rearrange this to get the concentration of A at time t by itself. And we can say that the concentration of A at time t is equal to the initial concentration multiplied by e to the negative kt power. Now this is only true for first order reactions because we started with a first order integrated rate law here. But what this shows us is that the concentration of A at any time t varies as a negative exponent of time t. And the concentration of A at time t decays exponentially then with time. So since it's negative, it's going to get smaller and smaller and smaller in an exponential way as time progresses. And that's what we see happening with nuclear decay. Here's an example. As a natural process, carbon-14 gets produced in our atmosphere. And of course, plants are breathing in some carbon dioxide and absorbing some of that carbon-14, and animals are eating some of those plants or eating other animals, and they're getting some carbon-14. But once a living being dies, it stops absorbing carbon-14. Now the half-life of carbon-14 is 5,000 years. Now we said that half-life for nuclear decay of elements is first order, so it has this expression. So if we were to graph out the mass of, say, 100 grams of carbon and keep track of the half-life, knowing that it takes 5,000 years to get half of that, after the first 5,000 years, the 100 grams would turn into 50 grams. After the second 5,000 years, so 10,000 years total, that 50 grams would turn into 25. That's half of 50. After the next 5,000 years, that's 15,000 years total. The 25 grams would decay down to half of that, or 12.5. After the next 5,000 years, that's 20,000 years total. That would decay down to 6.25 grams. So we can say that if we go 1, 2, 3 half-lives, that's 1/2 to the third power, we have 1/8 of our original starting amount. 10 half-lives, that would be 10 times 5,000 years, or 50,000 years, is about the limit of where we could realistically measure any sample of carbon to determine how old something is. So carbon-14 dating is a way that archaeologists would typically date things that are going up to 50,000 years old. And that's well within the range of human civilization, so it's pretty common for archaeologists or anthropologists to want to look at carbon-14 as a way of dating something. Once a plant or an animal dies, it stops absorbing carbon-14. So we can take a look at the percentage of carbon-14 left in that particular sample. Maybe it's a piece of grass, or maybe it's a bone fragment or something, and we can typically date how old something is using radioactive decay. Now for things that are older like that, say like a dinosaur bone, for example, we would have to use radioisotopes that have a much longer half-life than 5,000 years.